All right, so this is going to cover pages 9 through 10 in your notes. So follow along, add some notes, and if you have questions, be sure to add some comments. All right, so we're going to start discussing how to develop these equations for projectile motion problems. And we're going to start all of these position equations with the same position equation that has been written on our big 5 wall here. It's V naught t plus 1/2 the acceleration times the time squared. And then we're going to apply it specifically to the horizontal and the vertical direction. So if we start here, so if we need to develop, and that's kind of one of those questions that comes on an AP exam, develop an expression. Start with the thing that's on your equation sheet. And then I can state that my acceleration in the x direction is equal to 0. And then the final step is I'm just going to plug this in. So horizontal position, I'm going to keep my x's here. And then I'm going to specifically say, okay, it's not just the initial velocity, it's the x component of that initial velocity. Remember, we're breaking it up into parts. Multiplied by the time, and then this whole term is going to go to 0, so I have nothing here. So that is my horizontal position equation, and you can see that it reduces to just our constant speed equation. So we see constant speed here. Acceleration is equal to 0. Our horizontal velocity equation, essentially, we just know that it's not going to change. So our initial velocity in the x direction is going to stay the same. All right, now we're going to do the vertical position. So instead of x, I'm going to be careful about my notation, and I'm going to say y, because I want to look at vertical position, and we're going to associate the variable y with vertical positions. And then I have my initial velocity, the y component of it, times the time. And then my acceleration, in this case, my acceleration in the y direction is going to be equal to the acceleration due to gravity down. So I'm going to put that negative sign in front, and 1/2 gt squared. So now I've developed a position equation for the vertical direction. So remember, up is going to be positive, down is negative. So if we have a negative change in position here, we got to be careful about the signs. So these are kind of our two go-to equations for position. And then the vertical velocity equation, if I start with this equation on my equation sheet, and again, I'm just going to plug in that the acceleration in the y direction is equal to minus g, and I'm going to recognize that now I need to replace this with the components. Then I know that the vertical component of the velocity is equal to the initial vertical component of the velocity minus gt. So we see accelerated motion here on this side and constant speed on the horizontal side. All right, so it's important to identify all these letters that we've written out here and be sure that we understand what we mean by a component and what is like the real position and real velocity. So x is going to stand for our horizontal position. V naught x is our initial horizontal, and I'm just going to abbreviate the horizontal with an h, velocity. Y naught, or y with a sub-zero there, that is going to stand for our initial vertical position or height. Again, we can kind of remember that means height. And then g, of course, is going to be the acceleration due to gravity. I think we should all be good with knowing that one. Y is going to be our final vertical position or a final height. This is going to be our initial vertical, and I'll put a V for there for vertical velocity. And this is our final vertical velocity. And of course, T stands for time. So we want to make sure that we understand what the zeros mean here. It's usually pronounced a naught, and that is going to mean an initial. And if there's no 0 there, this just means that speed at that time, whatever time is associated with the equation, the speed at the time. So it could be time to the top or time to the bottom or whatever you are interested in. Okay, so here's a quick demonstration of that whole idea of balls that are launched horizontally and balls that are dropped straight down. hitting the ground at the same time. And again, this is just a repeat video, and I think we can maybe do a little stop motion within VoiceThread. But if you look at this ball on the left, goes straight down, and the ball that is launched horizontally is going to hit the ground at the same time. Why? Because in either case, they accelerate downward at the same rate. Both spheres are going to have the same initial y component of the velocity. They both have initial vertical component equal to 0, and then gravity just accelerates it downward at a rate of 10 meters per second every second. So they will cover the same vertical distance in the same amount of time and hit the ground at the same time. All right, so I hope you took the time to just take a quick look at that video of launching an object, two objects at the same time. One gets launched projectile here, and then one comes straight down, because this is a really big idea that it takes the same amount of time for it to go vertically down as it does to take this parabolic path. So we want to see that what variable is the same for both the horizontal and vertical equations. So when we look at all those equations, it's the time. It's the same t. There is no component of time. Time is the same on both sides. So the term range is also kind of expressed like how far does something go. So if the question is asking how far or asks for the range of the projectile, that is asking for the displacement in the x direction or the horizontal direction. And then of course the height, that is this guy right here, that is looking at our change in y, so the vertical displacement here. Again, a lot of vocabulary, a lot of letters, a lot of velocities running around here. We need to make sure that we kind of get a handle on an initial velocity, which is an actual speed of a projectile, v, which is the speed of a projectile at any given moment, but that these things are made up of components. So we could also have initial velocity in the x direction, initial velocity in the y direction, velocity at any time in the y direction, and velocity in the x direction. These components, see, look at all these v's. There's like crazy amounts of them. There's 5 of them, and we have to keep track of them. Remember, when we get back to it, it's all about the vector sum of those components that we have drawn before. So this is our y component and an x component. We're just breaking up these pieces into the parts. All right, the next questions we're going to answer with a little simulation on the next slide. So watch the sim on the next slide, and we can answer these questions. All right, so we're going to get to the answers of these questions, these conceptual questions. We're going to check the same initial speed here that it's going to go at, and then we're going to fire these projectiles with the same initial velocity, and we're just going to watch where they land. So again, we're going to just do a ground-to-ground problem. So we're just looking at where it crosses this horizontal axis here, and the winner for the maximum range is going to be the green one. It's the 45-degree angle. Will give you a maximum range for a ground-to-ground problem. So a good conceptual thing to know. You can add that to your notes. And then the second thing is the interesting thing about complementary angles. So if you recall, a complementary angle is any angle that adds up to 90 degrees. So in this case, the 60-degree plus 30 degrees, that adds up to 90. So these are complementary angles. And look at that. They land in the same spot. So complementary angles will have the same range, but of course, the 60-degree will take longer to get there, more time. All right, so now we're going to start getting into some of the numerical applications of solving problems with projectiles. And we're going to deal with 3 types of projectile problems. The first one is the simplest, and it's just a horizontally launched projectile. So what is that going to look like just diagram-wise? It just means when I take my projectile and I launch it, its initial speed is going to be all horizontal. So it's like the simplest case where my initial velocity is actually just the horizontal speed, and then it's going to follow this parabolic path as it gets down to the end of the ground. So that's essentially the diagram of what this is going to look like. Now we just have some different variables, and I'm going to add these to my picture just to kind of get a visual representation of what's going on. So the roof of the Chase Bank building is 125 meters above the ground. That's telling me how high it is. So I'm just going to label this on my diagram. That's the height of the building that it's launching off. And the ball strikes the ground 100 meters away from the base of the building. That's telling me how far it's going in this direction. So I got 100 meters in that direction. And then, of course, it's telling us just a reminder about acceleration. And the question is, how fast did the student throw the ball? So this is my question mark right here. It wants to know that. Now, the best way that I feel to tackle projectile problems, and again, these are the simplest problems we have, is to organize my givens in what I call an HV chart, which stands for horizontal and vertical. Because we have all these different velocities running around, we really need to organize our information. And remember, the horizontal side is our constant speed side. Our vertical side is where we're going to be using all our constant acceleration equations. So we need to organize ourselves, and an HV chart is the best way to do it. This is a great way to kind of, as you're getting started, to just jump off. All right, so let's start filling it in. So in the horizontal direction, I know this. I know that my change in the horizontal position is equal to 100 meters. The vertical direction, I know that I'm starting here. I'm going to call that position 0. I'm going to go down 125 meters. So I'm going to say my change in position in the y direction is minus 125 meters because I'm going down. All right, I know my acceleration in the y direction is going to be equal to minus 10 meters per second squared. So I know that acceleration. I also know that my initial velocity in the y direction is going to be equal to 0. And that's kind of an important thing. You're not told this, but these are the kinds of things you need to conceptually wrap your head around. That my initial velocity is going to be 0, and that y velocity is going to get bigger and bigger as it, of course, it accelerates downward. All right, and then what do we need to solve for? It's on the horizontal side. I need to solve for this initial velocity in the x direction. So notice one thing that's kind of missing around here is I haven't talked a thing about time here. So this might be an issue that I don't really know anything about time or the speed. So let's look a little bit at the solution. So the first question is asking, okay, what is this velocity? And the first equation you might jump into is, well, I know my change in position, that's equal to that initial velocity, or the velocity in the x direction, times the time. So I know this, I need to solve for that, but I don't have time. So this equation is not going to work for me right now. I have to kind of think, well, is there a way I could figure out how to calculate the time? And there is. And it comes from the fact of using what's going on in the vertical direction, and the fact that the time that it takes to go this horizontal direction is the same time it takes to go down here. We're going to take advantage of that. So I know the height, I know my initial velocity, I know my acceleration. I can look at my change in position in the vertical direction, E naught y times t minus 1/2 gt squared. And I've already kind of put the negative sign in there for my negative acceleration due to gravity. But notice this goes to 0 right there because it starts at 0. I know my change in height. I know the acceleration due to gravity. I can solve for time pretty easily. This is huge, all right, people, huge, huge thing. If I want to figure out the time in the air for a horizontally launched projectile, all I need to know is how high. Because the fact that my initial velocity is 0, this becomes a super easy problem. And we developed this idea with the workbook pages a couple of days ago. So I put in my numbers here. I have a negative change in position of minus, well, actually, let's just solve it here, and we'll plug numbers in at the end. So I'm going to have my negative change in y because I'm going downward. I'm putting my negative sign in here, and I'll put just the magnitudes in later. I'm going to multiply that times 2. I'm going to divide over by g, and then I have a t squared, and I'm just going to take the square root of both sides, and this is going to be a minus g in there too. So the negative signs will cancel out, so I get 2 times the change in height divided by g is going to be equal to the time. So I can just plug those numbers in. That's super duper easy. So 2 times 125 divided by 10, and I'm going to take the square root of that number, and that's going to give me my time in the air. Plug all that in, and it turns out it's a really super friendly number, and you get 5 seconds. And that is the time in the air. So next step, now we have the time in the air, we need to figure out how fast it went. So now we can go back to this equation right here, because now I've solved for the time, I know the range, and I can solve for that initial velocity that it was launched with. So my initial velocity in the x direction is going to be my change in position in the x divided by that time. Plug my numbers in, I get 100 divided by 5 seconds. That is going to give me a big time 20 meters. So I have gone back. So this ends up becoming a two-step problem. So if you think I need to solve for this horizontal velocity and I don't know what time is, 99% of the time, you're going to use the information on the other side of the table to solve for time first and then come back to it. All right, so you have enough information to head towards that WebAssign and do the first couple of problems that you've been asked to do. So go give them a shot, and we'll talk about them in class tomorrow. Oh, wait, but before you go jump into all that WebAssign stuff, I want you to sketch the graphs of the motion on the next page. So go check out the next page first. All right, I'm going to have you guys do this on your own. Notice that all of these graphs up here are all about the horizontal velocity, acceleration, and it says distance, but you can treat it as position. It's the same thing. And then V is going to be the vertical. So make sure that you kind of organize all these graphs together, use the scales that are provided, and we'll check the graphs when we come back tomorrow.